Start. But today's real topic, okay, what we want to get into is moving away from laminar flows and into turbulent flows. Let's kind of reorient ourselves with one more example before we... Okay, on fully developed flow. Oops. So let's consider a case where now water flows through a horizontal pipe driven by pressure. Okay, so it's a pipe flow driven by a pressure gradient. And we can assume that the flow is fully developed. The properties of the flow are as follows. dP dx, okay, that pressure gradient driving the flow is negative 2590 pascals per meter. The diameter of the pipe is 0.1 meter. The flow rate through the pipe is 0.04 cubic meters per second. The density, okay, water, we'll assume 1,000 kilograms per cubic meter, and viscosity, we'll go with 1/10. Do I have that correct? I do not. -3rd Newton second per meter squared. So a few things to find here. First, the mean velocity of the flow through the pipe. Okay, we'll call this U bar. The Reynolds number, the flow regime, and finally, what is the wall shear stress, tau W. So going through these one at a time. Right. The mean velocity is simply Q over A, so nothing complicated here. Just going to be the 0.04 cubic meters per second over pi over 4 times 0.1 meter diameter squared, which should give us about 5.09 meters per second. Now that we've got a velocity as well as a viscosity and a diameter, we can calculate the diameter-based Reynolds number, okay, rho U bar d over mu. It's going to be that 1,000 kilograms per cubic meter times our new 5.09 meters per second times the 0.1 meter diameter, all over 1 times 10 to the -3rd Newton second per meter squared. And this one's pretty friendly because we've got essentially a bunch of ones and zeros, right? So we've got 1,000 times 0.1, so 100 over times 10 to the -3rd. So 100,000 times our 5.09 meters per second. So we're going to end up with 509,000 for our Reynolds number. Laminar or turbulent? Turbulent, right? Way turbulent. Well beyond that 4,000 cutoff. Okay, so for C, we simply say turbulent because the Reynolds number is way bigger than 4,000. And then finally, the wall shear stress. Okay, remember when we derived, we did that force balance on a little slug of fluid. One of the things I said there was that the force balance was valid for any fully developed flow, whether or not it's laminar. Okay? We did it in the laminar section, but it's actually valid for turbulent flows as well. So we had this equation that said that tau W is equal to delta P times D over 4L. Okay? And this is valid for any fully developed flow. Well, in this case, we've got, right, delta P over L times D over 4, which is going to be our negative 2590 Pascal per meter times 0.1 meter over 4. We're going to end up with 64.8 pascals. Negative sign there to indicate that it is acting in the negative direction that's negative with respect to the flow. So a little rapid fire calculation of some flow parameters through a pipe. So this is the first one we've done numbers with that ended up being turbulent, but we didn't use anything about the fact that it was turbulent to actually arrive at this answer. Okay, I want to emphasize that. In doing this problem, we used only the knowledge that the flow is fully developed, and then our notional slug of fluid, right, that we said has the wall shear stress acting on it, pressure acting on it, and the fact that those two things have to be in equilibrium for a fully developed steady flow. Okay, and that led to that delta P over L equal 4 tau W over D, or 2 tau W over R. Okay. So the same approach, okay, doing this for the same theoretical approach also told us same force balance showed that the shear stress, okay, as a function of R was equal to tau W times 2R over D, okay, which says that the shear stress goes from 0 at the center line of a pipe up to the value tau W at the wall of the pipe. This is important also because though we derived this in the section for laminar flow, this also applies to turbulent flow. So I want to emphasize, it doesn't matter what flow regime you've got, the wall or the shear stress distribution in a pipe is always going to look like this. Okay. Increasing linearly from 0 out to the wall of the pipe. Okay, now what we did do in laminar flow is we said, all right, well, we know something about the way that this tau, okay, the shear stress, is related to the velocity gradient, okay, for Newtonian fluid. And then from there, we were able to leverage that knowledge to come up with a differential equation that looked a lot like a partially solved Navier-Stokes, and we integrated that once, and we got a velocity distribution. Great. Problem is that doesn't work that well for flows that are going to occur in flows of engineering significance. Flow is not that often laminar unless you're talking about pumping asphalt or molasses or corn syrup. Okay, when you're talking about pumping air or water through large-scale engineered piping distribution networks, it's typically going to be turbulent. Oops. I'm afraid I forgot to outline what the objectives for this lecture actually are, so let's quickly do that now that we've motivated it. We want to be able to explain differences in fluid motion between laminar and turbulent flows. We want to be able to explain why what we call Reynolds stresses cause turbulent flows to be, or to have more shear stress. And describe the distributions of velocity and shear stress across a pipe cross-section. Okay, so this is all kind of qualitative stuff. Yeah, this lecture, because turbulence is a fundamentally unsolved problem, we can't get really mathematical with it. So what I want to accomplish today is to kind of tell you why it's complicated, what we do know about it, and then equip you with some tools that you can use to at least approximate some characteristics of turbulent flow. So we understand at this point only that if you increase the velocity of flow through a pipe, it'll go from laminar through this transitional regime where it starts to show little turbulent bursts, and then finally into fully turbulent flow. Okay. A probe placed into a turbulent pipe flow. Okay. So let's imagine we've got, turbulent flow through this here pipe, and we install a little velocity probe that is able to measure all three components of velocity. Okay. This probe will register we'll call them mean and fluctuating velocity components. Okay. And so what I mean by that is, let's take a look at the as a function of time, what the u component, okay, the x component of velocity would look like here. Okay, so it would look something like this, right? And so we choose to say that, all right, this has an underlying average direction. Okay, if we looked at this and said, all right, is the flow going to the left or to the right? I would say, well, it's going in a positive x direction. Okay, it's moving to the right, but there's all these fluctuations superimposed on top of that average. So we say we strip out an average. Okay. And we say that u is equal to u bar plus u prime, right? Where this u bar is this average component, and the u prime is the fluctuation about that average. Okay. So if you were to take the average of this u prime, you get 0. Okay, because the idea is that it itself is going plus minus, plus minus, plus minus, because it's bouncing around the average. So it's the sum of these two things that gives you what the actual velocity looks like. Okay, so this is the x component. In the y component, we'd have v is equal to v bar plus v prime. And in the z component, we'd have w is equal to w bar plus w prime. So this is a decomposition of the velocities that leads to, if you were to plug this into the Navier-Stokes equations, you would arrive at what's called the Reynolds average Navier-Stokes equations, which is what most computational models are based on. We're not going to go into that kind of depth, but what I want to introduce is this idea of what is called notion of what we call turbulent intensity. Okay, and the turbulent intensity is given by a cursive capital I. Is given as the RMS of the fluctuating component divided by, okay, the mean velocity, u bar. So it's the square root of u prime squared, okay, averaged all over u mean. So in a way, it's saying like how much. It's saying how much of the kinetic energy in a flow is focused in this fluctuating part, and how much is focused in the bulk average flow. Okay. So low numbers indicate. Okay, a low number would indicate that the fluctuating component is vanishingly small, which would mean that the flow is approaching something like laminar. Okay, that it's very steady. A very high number indicates that the flow is extremely turbulent and the fluctuations are dominating. Okay, that most of the kinetic energy is buried in those fluctuating parts. So for things like a well-designed wind tunnel, I think these are numbers that are in the book as well. So things like good wind tunnels will typically have ranges of around 0.01 to 0.0, oh sorry, this should be 0.002 to 0.01. Okay, so about 0.2% to 1% turbulence intensity. If you look at things like rivers, oceans, or atmospheric flows, you'll have turbulent intensities greater than 0.1. Okay, so what do these turbulent fluctuations do? Okay. Well, what they do is that they tend to be very good at mixing things. All right, and I've got a little video to show that sort of demonstrates this. This is from a conference that I attended. Oh, is it not going to show? Hold on. There we go. This is from a conference I attended where the whole idea is they can come up with really cool videos that explain some turbulent or some fluid dynamics phenomena. So this is a big tank. Okay, that they towed a flat plate through, and they used what's called particle interval symmetry. It's this laser-based imaging system that looks at little specks floating around in the flow, and they measured the velocity right along the edge of this moving plate. So that little box up at the top shows kind of where they are on the plate. And the thing about this is that they have, the plate is moving fast enough. Okay, you can see the instantaneous Reynolds number down here going up, but it's moving fast enough that they achieve turbulent flow. And so this is showing here that component of U prime. Okay, where you've got those fluctuations. And so you see these sort of packets that are being moved along. But what I want to emphasize here is a little bit further down in the video. Here we go. So then they took those data and they injected them into a computer program, and they said, okay, we've got velocity fields, so let's kind of semi-model what those velocity fields would do in terms of like mixing up if we injected some dye into the flow. So they used experimental data to kind of approximate what this mixing process would look like. And so here's sort of semi-empirical mixing behavior of this dye. And what you notice is that as the Reynolds number counts up, okay, that more of this dye is getting kind of thrown around and churned by these turbulent fluctuations. And then here's another one where they instead seed the flow with this kind of grid of particles and then model what it would do to that distribution of particles. And so once again, you see that some particles are being kind of sucked in by those fluctuations. Some are being ejected or thrown out by those fluctuations. But the key is that it's doing a really good job of mixing around across that boundary layer the portions of the flow. Okay, so the reason that this is worth pointing out is because, right, so we saw examples where it was good at mixing up particles, it was good at mixing dye, but those are scalar quantities, right? Those are things. We've also talked about how transport for a fluid, it not only applies to, like dyes and concentrations, but also applies to things like velocities or momentum. So what happens in a turbulent flow it's good at mixing, right? Concentrations, things like right, temperature distributions, but also momentum. And so if we consider a pipe, once again, I want to consider first a laminar boundary or laminar flow. Okay, so we've established that a laminar flow looks like this. It's this parabolic. Here's laminar flow. A turbulent flow is going to look a lot like this. Oops. Okay, it's going to be much flatter. And the reason for that is because all that turbulence, what it does is, if we have a laminar flow that becomes turbulent, those turbulent fluctuations are going to do a really good job of spreading out this momentum across the distribution of the pipe. Okay? It still has to obey that non-slip boundary condition at the edge of the pipe, so it has to decrease to 0 here. But as you move away from the wall, really quickly, that mixing action is going to do a good job of it distributing that distribution of the mean velocity. So shear stress in a turbulent flow does not obey our tau equal to mu du dy sort of formulation. Or at least, I shouldn't say that. It does obey that. Let me rewrite this a little bit. Should say that for a laminar flow, right, we've established that tau is equal to mu du dy. For a turbulent flow, we might be inclined to say tau is equal to mu times du dy, right? The mean velocity, which is actually what's drawn here, okay, bar. But that isn't the case. And that's not the case because it ignores this sort of turbulent mixing that goes on that is spreading out momentum. So it's actually the mechanism of shear stress is a little bit different in turbulent flow. So instead, tau is going to be written as tau laminar plus tau turbulent. which is equal to, right, mu du dy minus rho u prime v prime averaged. Okay. So this represents, right, the laminar friction, that molecular diffusion, that rubbing of fluid particles against each other that begets friction. And this represents the turbulent mixing that occurs. And finally, u prime v prime average is always going to be less than or equal to 0. Okay, this can be shown by some more in-depth analysis. So, right, tau turbulent is always going to be greater than or equal to 0. What this means is that the shear stress in a turbulent flow is always equal to or greater than the shear stress in a laminar flow. Okay. And I think we're going to be running out of time to get to the last few concepts here. So I think I'll probably leave those until Wednesday. Quick announcement before we depart. I'm actually not going to be here in person on Wednesday. I'm going to be, lecture will be delivered via podcast. Maybe I'll record it and watch it. Please do watch it because we're going to need to know this stuff for Friday when we start dealing with dimensional analysis of flow for types, or getting into more in depth in the dimensional analysis of flow for types. So I'll let you know when that's posted, and I'll see you guys in person at the end of the week.